So we already have the 12 volt electrics working in the van, but this time we're going to be setting up our inverter, so then we'll be able to power the 230 volt AC sockets as well, so we can just plug in any normal appliances we need when we're on the road. So this is the electronics diagram we've been using for the whole build, and we've done now everything apart from the AC side. So we've got solar panels on the roof, which is charging our batteries. We've got our 12 volt fuse hub, which is powering all of our 12 volt appliances like the lights and the fridge and the fan and things. And we've also got a DC charger, which is allowing us to charge our batteries when we're driving the van from the alternator. And that's all going via this Links distributor, which is just like a big hub for everything. But we've never done, up to now, the AC side, which is this bit here. So that is the inverter, and all that is just taking 12 volt DC and converting it to the 230 volt AC, which you need to use a normal 3-pin appliance, and then powering the actual sockets. And then just in the middle there is also a breaker box and RCD, just to provide a bit of safety. Most of the stuff in the van we want to power off the 12 volt side, because that is the most efficient for us, because anything that goes through the inverter has a little bit of an efficiency loss to get it up to 230 volts, and most things you don't need it anyway, like the fridge is a 12 volt fridge, our max fan is 12 volts, all the lights are 12 volts, so there's actually not that many things that we need to plug into the inverter, but it's things like if we wanted to use some cooking appliances when they're on the road, Abby's hairdryer and stuff like that, and also probably my laptop charger. Even though my laptop can charge on 12 volts, the power brick just works a lot better if it's actually plugged into a 3-pin socket. We've ended up going for a 1000 watt inverter, and that's just because we figured that's more than enough that we need to power everything that we want. And because we're going to be wiring it to 3 sockets, we can also power a few different things at the same time. And then there's also 2 different main types of how they generate the power. So you can get what's called modified sine wave and also pure sine wave. So pure sine wave is pretty much exactly what the AC supply looks like coming out of your house, so anything that powers your normal 3-pin appliances, and that's a really nice smooth wave like that. Modified sine wave is sort of the same, but it's just an approximation to it, and it's a cheaper way of doing it. So as you can see, it kind of looks like a wave, but is not perfect, and that will work for some things, but other things it can cause problems with sensitive electronics and stuff like that. It can make things run slightly inefficiently or get a little bit too hot. So we wanted to go for something pure sine wave, and if you've got one that does that, you can pretty much just plug in anything and you know it's going to work just like it would in the house. And you might have noticed we've also got 2 inverters here. The reason for that is we originally bought this one and we have actually used it, but now we want to do a more permanent install and get it into the van wired up to some actual sockets in the van. And we decided that the Victron would probably work best for us in that case. And it's quite interesting as well because they're both 1000 watt inverters, but this one is quite light, and this one is way heavier. So this one, obviously it's a bit awkward to measure it exactly, but...
And it is attached to 2 pieces of wood as well.
Yeah, but that's coming up just over 3 kilograms. Whereas this Victron one, put that on, I mean, okay, it won't even measure it. So yeah, 7.7 kilograms. The reason it's so heavy that we found out is because this one is what's called a high frequency inverter, and this one's called a low frequency inverter, and the low frequency ones have a huge iron core, iron transformer inside, which gives it the weight. But the other thing the iron core does is it makes it really good at devices that need a lot of surge power. So if you've got something that needs a lot of power just at the start, so you're turning on like a big motor, you might need a lot of power just for a few seconds. But that's not actually the reason we ended up going for this one in the end. This one should be better suited for us to hardwire into the sockets we have in the van, and not just use the single socket that's on the back. And the reason for that is one of the things that's on the inside of it. Then the cover just comes straight off, and straight away you can see the absolutely huge iron transformer that's inside it. And you can see as well that conceptually the inverter is actually fairly simple really. You've got positive and negative DC power going on this side, and then just goes through the inverter, through the transformer, and then just comes out the single AC socket on the other side. This one we think has better provisions for us for changing the way the earthing is done in the inverter. so that it's better suited for hardwiring it into the permanent sockets we're going to have in the van. But huge disclaimer on that, so we're obviously not electricians, and everything that we've done with the electronics in the van with the 12 volt stuff and that we're going to do with the inverter and wiring to the sockets is just based on all the research that we've done. Lots of resources like this, the Wiring Unlimited guide from Victron, which goes into detail of a lot of stuff quite specific to mobile installations as well, which is good. You get this as a free PDF download. But yeah, there's obviously lots of information out there and lots of different standards depending on what country you're in as well. So we're trying to do everything as best as we can to the UK standard. So yeah, if you're doing any electrical wiring in your own van, then obviously make sure you're happy with what you're doing, and if there's anything you're not happy with, then it's best to just get help from an electrician or someone who knows the electrical code in the country, because particularly with AC electricity, it's not something you want to mess with, and inverter earthing is a whole massive minefield, which we found out, and there's a lot of information out there, so quite hard to digest. So from what we understand about these types of inverters is that they're only actually designed to power a single device at one time, and that's why they also only have one physical socket to plug in something. And the reason for that is they're set up as floating systems, which means there's no reference, there's no connection to earth. And obviously we're in the van, so we've got no normal earth connection anyway, but we've got the van chassis, or if we had shore power, so if we were hooked up to the grid, then we could also be plugged into the earth connection ultimately in the electric supply. But if we're just using it isolated in the van, then you've got an isolated floating system. And that is fine if you're using just one device. So you can see that in the Victron guide here. They've got a whole section on mobile earthing setups using inverters, which is quite nice. And you can see in this example there's just a generator or an inverter, and there's no connection to earth, there's no reference to the chassis or anything like that. And that means if this unfortunate person comes into contact with the live wire here, then actually they're not going to get any current flowing through them, and they should be okay. Obviously it's not something you want to try, but by touching this wire they're not going to get any shock. And similarly, if they touch the neutral wire, then they're also going to be okay, because there's no current flowing again, there's no complete circuit. But obviously if they touch both wires at the same time, then they are now completing the circuit. They're effectively acting like the wire, the last bit of the circuit, and all the electricity is going to go through their body, and it's not going to be a happy ending for that person. And that all kind of works quite nicely. The difficulty comes from if you plug in multiple devices to them. They're not really designed for that, and you can create scenarios where it's actually potentially unsafe. And the reason for that is it also depends on what types of devices you're plugging in. So every device you can get that's got a 3-pin plug on the end, and similarly for other countries as well, has one of these different classes, and that tells you how that appliance works in respect to the earthing that's inside. And what they look like is a class 1 device is something like this, standard kind of household cooking appliance, which is generally got a metal casing, although they might not necessarily have. And because obviously the metal is conductive, if there was a short in the cable inside here and the live wire came into contact with the case, then it can obviously energize the outside of the casing and become live. So what there is a separate wire inside called the earth wire, and that is connected to the outside of the casing, and then that goes back through the plug, through the big pin, which is the earth pin, and then takes it back to the electric supply, which would then hopefully trip the breakers and cut the supply. And that's got this little symbol, which is a little earth symbol there, and you can just see it on the plug there. But then we've also got class 2 devices, which are sometimes called doubly insulated as well, and the symbol for that looks like 2 insulated squares. And my phone charger is an example of something like that. And what that means is there isn't actually an earth wire inside here, because it doesn't need one, because the outside casing is completely insulated. It's got 2 layers of insulation, which is why it's called that. And so the earth pin on this one is actually completely dummy pin. It's just made of plastic, it's not a real one. And these ones are actually a little bit safer than the class 1 devices, because even if there was a short inside here, there's no way that I can get a shock from it, unless obviously you do something really bad and cut open the case or drill through it or something stupid like that. And so we were looking at the British standard for this, which is from BS 7671, and this is for mobile generators, but it's the same sort of principle for inverters. And basically it says, yeah, it's extremely important to note that you can only use it with 1 or more items of class 2 equipment, 1 item of class 1, or 1 or more items of class 2 and 1 of class 1. And what that basically means is you can use it with as many class 2 devices as you like, so as many phone charger type things like this, but you can only use it with a single class 1 appliance. And the reason for that is that if you had your class 1 items, so again the ones that usually have a metal case, and there was a short to it, that case then becomes live. But as we've seen, I can touch a live wire in this floating system and I'm not going to get a shock, but there's still a fault and you wouldn't know about it. So then I think the key thing is, if you then had a second device plugged in, which was class 1, and if that, for example, had a fault, then you could be touching both at the same time. So I could be holding the kettle or touching the kettle while touching a toaster or something, and then if there was a fault scenario, then it could complete the circuit and then current would obviously go through me, and that would not be good. So whereas with class 2 devices, you can't really have that problem because they're all insulated really well. So if you do want to use multiple class 1 devices, then what it says you need is an RCD to provide protection. And an RCD is just a device like this, and all that's really doing is just making sure that the current is not going where it shouldn't. So if the current doesn't go in the circuit in the normal path, it will detect that and it will trip and cut the power, hopefully before it causes any injury or worse to whoever's touching it. So we definitely want to have that kind of setup, because we're going to have multiple sockets in the van, and so we could in theory be plugging in multiple appliances at the same time, and we don't know exactly what classes they'll be. So the way an RCD works is it's just a little device which sits in between the live and the neutral wires, and all it's doing is just checking all the time that the amount of current that goes out on the live is exactly the same as what comes back on the neutral. And if ever there's a situation where the amount of current that going out on the live is different to what's coming back, so for example if there was a device here that was faulty, then some current might go back through the earth wire, and then obviously what's coming back through the neutral will be less, and so it will sense that, and it's very sensitive and will trip straight away and it will cut the power. But if you don't have the earth wire there, then it can't work, because the only way for current to ever get back to the source is to go via the neutral wire. So if you have an RCD in a situation like that, it won't actually do anything, it's completely useless. So I could be here touching both the live wire and the neutral wire, and as far as the RCD is concerned, it's completely happy, because I'm effectively just acting like a device in the circuit and current's going out through me, the device, and back. So in that case I am effectively the toaster, and probably I end up toast. So that's not something we want to do. So we want to have an RCD that's operational, and in order for that to work we need to have also this bond, it's called, between the neutral and earth. So you have to connect them together so the RCD can detect the imbalance, and that ultimately is why we've decided to go for the Victron inverter, because this one actually has a little jumper that you can move and it sets up this bond for you so that it'll work with an RCD, whereas the Renogy inverter doesn't have that functionality built in. So if we wanted to set up that bond, we'd have to do it separately in the consumer unit or something, and that's not something we wanted to do. We prefer to use something that's just actually got the provision to do that. There we go, all mounted.
Phew. What's next?
Now we need to get the consumer unit in there.
Right.
So it should fit quite tidely in there actually, it's worked out pretty good.
There we go. Yeah.
So this is the RCD that we've gone for, and yeah, what this does is it basically detects if there's any current that's leaking out of the system and potentially going through a person, and it doesn't take much to actually really injure yourself with that if it goes across your heart. So even something as small as 1 milliamp, which is nothing, is enough to actually feel it, a bit of a tingling sensation, and it varies obviously depending on different people and stuff like that, but as a general rule of thumb, even 10 to 20 milliamps, which again is really not much at all, is enough that you already can't let go. So yeah, you don't want that, and once you start getting up beyond that, it gets to the point where it can obviously be really bad and potentially fatal. So yeah, what this does is it detects that and then switches, hopefully straight away, pretty much, so that you don't have any problems and you live another day. But there is quite a lot of types of RCD as well, and those are here, and they all have different symbols on them. So these are the 5 main ones. So AC is the oldest type, and that I think it's called AC because it literally only detects alternating current. But these days, quite a lot of devices actually have some DC components in as well. So if you've got something that has an electronic circuit in it, so like a washing machine, it might have an AC motor inside, but it's also probably got a DC part for all of the control panel with all the timers and things like that. So that means you can actually get a little bit of DC, and for the RCD to be properly effective, it should be detecting a little bit of DC as well, and that's where the type A comes in. So that gives you the same as the one before, so as you go up the rankings you get everything from the previous one plus something else. So the type A also detects a little bit of pulse DC, which is what that one is. Then you've got type F, which is the same but also with high frequency. So normal AC system in the UK is 50 Hertz, and what that means is that this sine wave is the voltage changing, and it goes up and down 50 times every second. But if you have something that has a higher frequency, then potentially the RCD might not detect that. So F allows you to detect really high frequency stuff as well. And then you have B, which can detect actual full DC current. And then B+, which is a little bit rarer and goes on to detect even more stuff, really high frequencies. So we were thinking maybe we'd put a type B RCD on there, which detects obviously the DC current. And from what we've seen, actually we don't need it, because even though we've got DC and AC here, in our particular inverter there isn't a path for the DC side to actually ripple into the AC side, which means that for us we think we're okay using just the type A RCD, which is good because it's a lot cheaper. The next thing is the MCB, so that's going to go side by side like that, and this one is detecting leaking current to stop any harm to us operating it as humans, and this one is detecting overload and short circuit to actually protect the wires. So the two devices for two slightly different things. This one, the MCB, is basically just like a circuit breaker. It's just like a resettable fuse, and again for that one there are different types you can get, so it all gets very confusing. But basically the way it works is there is actually two parts inside. There's a bimetallic strip which heats up when it's overloaded. So this one's rated for 10 amps, and if it goes beyond 10 amps, the strip will start to heat up, and it's not an instant thing, but if it keeps being overloaded for too long, then that strip will heat up to the point where it actually trips a switch and it cuts out. And then there's a more instant part which is magnetic, and that trips really quickly, and there is a rating on here, a letter. So this one is B, and that corresponds to how quickly or how much current it takes for that second part to trip, which is something that's maybe a little bit counterintuitive, but yeah, this one won't actually trip until you put 30 to 50 amps through it. And then when it does get to that point, it's very fast on that part. The reason for that is actually by design. If you've got something that takes a lot of power to start up, you don't really want it to trip at exactly 10 amps, for example, because it'll just be tripping all the time and it'll be a nuisance. So it gives you a little bit of a buffer and then trips. So as you go up, if you've got something that needs a huge amount of surge power, then you might go up the MCB types. But for us and for most residential stuff, B is completely fine. And the last thing with it is the RCD also has an amp rating on it as well. And this one is 63 amps. And basically that just needs to be big enough to handle all of the expected load from the downstream MCBs. So this being 10 amps, the 63 amp is fine. And the reason as well, you might have noticed, we've gone for a double pole for both of them. What that means is both of these take the live and the neutral at the same time, so they are actually switching off both wires simultaneously. And in the house you probably wouldn't get that most of the time, but because we're in a camper van, you can get issues, especially if you go to Europe and stuff, where you have potentially the reverse polarity, which means that you might be at some campsite or something and they've got live and neutral the other way around from what you're expecting, and that can cause a lot of problems. For us, it's actually never going to happen like that, because we can't plug into shore power. We don't have that facility, so we don't have to worry about that. But it seemed like it was a good idea to, because we're in a camper van, just go with that anyway, and it's better, it's safer. So we've got double isolation switch off on both of those things.
So our power is going to be coming out the socket on the side of the inverter here and just coming around and inside on the right hand side here. So we're going to put the RCD on the right hand side because that's the one you want to go to first, and then the MCBs after that. Don't to break it. Oh, okay. There we go.
Tick that off life's bucket list, wiring your first plug.
Yes, I can, can't I?
So the first thing is it's going from here through the wire, and then it's going to go into the RCD through the bottom, and it's going to come out the top and then jump over down through the MCB, and then through there, and then back out to our sockets.
Probably some fiddly wiring about to occur, right?
Looks like it. And it's quite low down as well.
Yeah.
Cool, so the live is going to go in that one, and then the neutral. There we go. Just big enough.
How's it going?
Not too bad. Just added another grommet in here, drilled another hole through that bit, because yeah, realised we have to get both of these cables through. This is the one that's going up to the socket by the bed, and this is going to the socket by the fridge. And we're actually going to wire all of the sockets in a radial pattern, so just going from one socket to the next and to the next, and then we've got 3 sockets, so only one circuit. But because that's up on the bed there, and it's pretty awkward to get cables up and down through the van metal and stuff like that, what we've decided to do is to just have both of those coming in here, and we're just going to join them inside the consumer unit, so they'll both be going into the same MCB. This is an interesting method you've got to electrical wiring.
I just thought it would be easier. Right.
But yeah, that should be all of the consumer unit wiring done now.
Okay, cool.
Hopefully the other bits will be a bit less fiddly.
I hope so. Right, so we're going to wire in our sockets now, and we've got 3 around the van. So we've got 1 3-pin here, 1 on the edge of the fridge there, and 1 just on the bulkhead wall over there. And we've gone for Burka sockets, and they're nice because you can use these frames and then just change out the middle to 3-pin or 12-volt or whatever you like, really. We've already wired in the 12-volt socket, just this one here, which has actually been really handy for charging our phones and things like that. But we've got a couple more around the van as well, which we need to wire in too. Okay. What we've done is made these panels completely removable. Obviously, because they're cladding, they've tongue and groove. We just got rid of the tongues to make it a lot easier in case we needed to access behind. So just
like now.
Yeah, exactly.
So now we're just going to make our way down and do all the other sockets, which is nice because we can finally tidy up this mess of wires we've had coming out the fridge forever.
For a very long time. Bye-bye.
So for this plug here, we need to get 2 sets of wires in them, and there isn't really enough space in the plug, especially when you add the little back box for it to do that. So what we're going to do instead is join it with a few Wago connectors, and we just got this little junction box which we were going to use on the roof when we did the internet antenna install, but we didn't need it, so it's quite convenient, and we'll just mount that somewhere in there behind the drawer. Just remembered it's probably better to actually put the socket through the hole before wiring it in. And that's the second time today we've done that.
Man. It's no good inside the drawer, is it?
These ones are just positive and negative, and what we found as well with these, when you put a normal spade connector on there, they make it extend out quite far, and it gets a bit tricky, especially when we've got like the drawer closing up against this. So what we got instead was these flag terminals, which are the same but just at a 90-degree angle. So they're pretty good, because then we can just put them on and they go straight down, so that keeps the wires tucked out of the way. But the slightly annoying thing about that is I had to buy a different crimp tool to use them, but I got this second hand on eBay and I think it was 99p, so
Result.
it works out pretty good. And the positive is the middle pin, and the negative can spin around here. There we go. Yeah, looks pretty good. Nice. That is all the sockets installed.
Yeah. That's surprisingly tiring. Ridiculous, really.
Very, very fiddly.
So, I guess we just got to make the cables for the inverter now, right?
Yeah, it's got to actually connect it up to the batteries and test it out.
And then that's it, right?
So for the AC wire, we've been using this stuff, which is 2.5mm squared, and it's also stranded, so it's good for in a van. You've got all the vibration and stuff on the road. You don't want solid core wires. And then for the DC side, obviously got to make some cables now to go from here to our links over there to actually power it. And for that, we're going to use 25mm squared cables, which is fairly chunky. It's just one of those annoying ones where we have to use the vice tool to actually crimp it because it's so heavy duty.
Oh, fun times.
But I think it's probably the last one we have to do like this in the whole van. Yeah. Actually, that's not true because we have to do the ground wire as well.
Oh, you got my hopes up then. Thanks.
But it will all be done after this project.
I don't know about you, but I think once we've done this, we probably should tidy out these wires a little bit.
Yeah. It's been on the to-do list for a while.
Yeah.
There we go. Into one of those. Jackson, I can see you. So everything's off, just covered up the batteries as well. And then the negative one is just going to go on there like that. So we've got a 100 amp mega fuse that we're going to use for this. And then the last one left is the ground wire. Bit of a tight squeeze, but that should, there we go, just go in there like that. And then the last thing we need is the little Bluetooth dongle. So this one just plugs into the back. Right, are you ready? Let's give it a test?
Yep.
Okay, so turn all the power back on. Probably won't be the most exciting thing. It's got power and it's got lit up LED.
Nice.
And you can see the Bluetooth has come on as well. So we should be able to see it in the app, if I can find my phone. Oh, there we go. New device. There we go. It's basically set up, and in theory you can plug stuff into the sockets and actually have them work. But before we do that, we want to just check that the RCD is working correctly. So at the moment we haven't actually changed the neutral earth bond inside. So what we're expecting actually is that the RCD shouldn't be functioning yet because it doesn't have that bond. And then the RCDs have this test button on there, so if I press that, then you can see it trips. But what's interesting about RCDs is that test button doesn't actually test really the whole circuit and doesn't prove that the RCD is working. What that does is just test that it electrically and mechanically works. So it tests that it can work, but not that it will work. So what we actually need to do is to plug something into a socket and then check that it actually trips. What we've got is this socket tester. So you can just plug this in and then it tells you if there's any problems with the electric supply, and also allows you to do an RCD test. And with that, if we push this button, then it'll actually simulate a fault and should trip the RCD. But we're expecting it not to work because it doesn't have the bond yet. So put that on, and now we can plug this into a socket. It's flashing the top circle, and that means there's a missing earth wire. And yeah, so basically it's telling us that the system is not completely correct. If you plug this into a system socket in the house, then you want it to say correct, and obviously that's what we want too in the van. So yeah, it is interesting because you do that and it works fine, but there's obviously an earth problem there. So now what we can do, if we actually press the RCD test button, then nothing's happening, it's not tripping. Right. So that means, as it's wired at the moment, it wouldn't actually trip if there was an earth fault. So the RCD in this configuration, even though it's doing that, is completely useless, and it wouldn't actually help us at all. So what we need to do is take the inverter off the wall again and move that jumper around and then put it back, and then when we do that, with no other changes, it should all work. So we just got to pull that one out, and then basically we need to move it from that pin to that pin. So if you've got an inverter charger, then when you're plugged into the grid, it uses the neutral earth bond from the electric supply, and as soon as you unplug from shore power and switch to inverting mode, it'll actually make that connection automatically using a relay, and any time you switch backwards and forwards between the two, it just turns on and off that jumper. But for us, with no shore power, we just make that connection once here, and then it should be good to go. Okay, so we've got it all set up again, and now second test. So we'll plug that back in, and then this part should be the same as before. So if we do this, then obviously it still works.
Yep.
Now we can go inside and do another test with this. Let's see what we get. There we go. Yeah, that's what we want to see. So according to this, everything is good, and the AC side is wired correctly, which is really nice. So now we can actually test to see if it trips the RCD. So this is the crucial test.
Right.
So you ready? So
shall I go down?
Okay. Then you press the button. You ready?
Yeah. Yeah.
Woohoo!
Yay!
Cool. Yeah. I don't know why, but just hearing that little click is quite satisfying.
Nice.
So we've just added some ferrules on here just to tidy up the wires in the consumer unit as well, and that's because we're using fine stranded cables, so without a ferrule on there, when you screw down this screw onto them, it sort of crushes the wires a little bit. And then we've also added a separate earth wire just for the consumer unit, which goes to the chassis on our ground point there. And the reason for that is just to satisfy one of the British standards that just says that the chassis needs to be bonded to the main earthing terminal. So that's a 6mm tri-rated flexible earth wire. So we've got correct coming out of that one.
Nice.
And then we check this one as well, guarded by Jackson. All sockets are correct and working. So yeah, now we've actually got to plug something into test.
How many watts is this, Tim?
I can't even remember. It's ridiculously low power.
Not many.
It's not going to put it through its paces very much, let's put it that way.
450 watts. There we go.
First test.
Yay!
Nice. That is very cool.
Wow.
This is nice low power, so there you go.
Yay, nice.
You can have a little lamp by the seat there.
Nice, nice.
Quite handy. I've got a kettle. There
that kettle is what, 650 odd?
Something like that, yeah, it's just a little travel kettle.
Right.
So that's on. Got one more socket, so just plug in my laptop over here.
And it's charging.
Here we go.
Right.
And the kettle's starting to boil, so.
With those three things, what's that drawing? 663?
Yeah, so we've got a bit of capacity left.
So yeah, we've got one more finale thing to try. And I'll just say this now, we are not planning on having a microwave in the van, but we just thought we may as well give it a try. Funnily enough, it says the word inverter on it.
It does.
And we thought, oh, what can we use to test the microwave? I know. Let's eat some popcorn. 2 to 3 minutes. This side down. 2 minutes on low. Hey, there you go.
That is cool. That is not the sound that I thought we'd ever hear in the van.
No. Usually a popping sound doesn't mean anything good, does it?
It's true.
You can start to smell the popcorn aroma.
There we go.
That is your first, and probably last, van cooked microwave popcorn.
Tasty.
Yeah, that's pretty good. Well, I think that's about as much as we can do on the inverter, so
Pretty much.
I think that's it for this video, isn't it?
Yeah, I think so.
Yeah.
What are we getting on with next?
I'm not sure.
Either the gas, or we might get our recirculating shower finally working.
Yeah.
Don't
Two
know
big projects, we haven't decided which one.
Yeah.
But
We'll see you in the next
we'll
one.
see you in the next one.
Bye, guys.
Bye.
Give us a like and subscribe below if you enjoyed this video, and we'll see you next time.